Hi, I'm Randall Heyman, and this is video number about 160 in my coronavirus videos. If you'd like a video made for you for free during the coronavirus, then just contact me by commenting below any of my videos or emailing me. So this is for, I'm not sure how to pronounce this, Mahlatse. So thanks for your comment. He or she asked me to explain connectedness. So this is a little bit vague because well, let's just start writing some stuff. The first issue is that there's different sorts of connectedness in the area of analysis. So here we're talking metric spaces, topological spaces, open sets, closed sets, or that sort of thing. So we have so I suppose a set can be connected totally connected path connected etc. So what I'm saying here is that there's more than one concept of connectedness, and I've illustrated three here: connected, totally connected, path connected. I'm just going to go through today connected. Probably the next most important is path connected. So if people have got more questions, they can just comment and I'll see what I can do. Okay, so the second point I wanted to make is that I'm going to be talking for Mahlatse in terms of, so I will use metric spaces, but everything applies to topological spaces. So I think I've made this point before. When we talk about analysis, we start off often with the real number line or just R2, which we can represent with a chart, a Cartesian plane. But then we quickly move on to metric spaces, which are a generalization of that. And then beyond that, we generalize even further to topological spaces. But for my terminology, I'm just going to talk in terms of metric spaces. I'm sorry for all these little notes first, like 1 and 2 here, but I wasn't sure where Mahlatse is in his learning. So, okay, so now let's go to a definition, or definitions actually, because we'll need to first define when a set is separated. Okay, so a separation, sometimes also called a partition, but a separation of a subset S of a metric space X is a disjoint pair T1, T2 of open sets. That open is very important. Open sets in X with two properties. A, the intersection of T1 with S must be non-empty, and the intersection of T2 with S must be non-empty. And B, S, the set S must equal the intersection of T1 and S union the intersection of T2 with S. And subset of a metric space is connected if it has no separation. So there's a fair bit to take in here. Let's just underline a thing. So the important thing here is a separation, which I've spelled incorrectly. So that's a good start, isn't it? Separation. I've probably done it throughout, have I? Separation. So yeah, done it again here. Separation. Okay. So there's a fair bit to take in here. This is all a bit complicated. Yeah. The easiest is actually, the easiest thing to do is to start out with is probably to, so here's the example, S is equal to X is equal to, let's call it R, the real number line. So the easiest case initially is where you just have, where the subset is actually the set itself. So the question is the real number line, I'll draw it, is the real number line connected? I'm not going to, I don't think I'll do any proofs here. I'm just going to go through to so that we get the idea. So here's the real number line. Here's 0. And is this separated? Well, can we separate it? Essentially, that's the question. And so the question would be, can we create two open sets that are disjoint, so they can't overlap, and yet together they cover the whole real number line. So we want to, let's write here, we want to, if for separation, find T1, T2, such that, well, the first thing is that T1 and T2 can't intersect. And then the second thing is that T1 union T2 must equal the whole set R. This just makes it a lot easier because we can see that that's not possible. I mean, let's just take, we'll call this T1. Well, how are we going to put T2? If we put T2 here, well, sure, they're disjoint, but they don't, the union of T1 and T2 doesn't make up the whole real number line. So we can't do that. So that won't work. The next thing is that if we look at the point here, so if you direct your eyes down here, where does T1 intersect with the real number line here? Well, you can see that that's a point. I can't draw T2 going through that point because if I did that, well, I suppose I could do that. So let's make T2 go through the same point. So that's not going to work either, is it? Because sure, the intersection of the two is the empty set, they're disjoint, but when I take the union, I don't include that point there. This point here is not included because it's not part of either of the open sets. Open sets do not include their boundaries. So I should actually rub that little bit out there. A bit hard to rub out now. So that's not going to work. So we've tried where they're sort of completely, obviously sort of disjoint. That was the first case. Now let's do this. We've done the second case where it actually intersects. I better patch this up, I think. Well, I didn't intersect where the open set lines intersect at one point. And now the the other way to do it, then I suppose the third possibility is this. And now we have included, the union is correct. It includes the whole real number line, but they're not disjoint. So in this case, what can we say? The real number line cannot be separated. Well, because it can't be separated, we can then say it is not connected. Sorry, it is connected. Is connected in itself, in the real number line. Okay, so that's one example. Let's do another one. 5. What about the integers in R? Okay, so let's draw that. We'll be about there. Should be a bit lower. Let's make it a bit lower. There, that's better. Whoops. Okay, I'm going to try and draw a bit better now. Okay, so here's the real number line. We can actually draw in some of the integers. -2, -1, -2. Okay, so can we separate this? Well, yes, we can separate this, because what I can do is I can make, let's go, in fact, let's do this. Let's go, this is the open set T1. And we can just make T2. So this here is we can just make T2 like this. You might want to think about this point down here being the square root of 2, for example, or you could actually make it 3 on 2, even simpler. So let's make it 3 on 2. So here, what can we say? Well, in this case, T1 intersection T2 is the empty set, and T1 union T2 is the integers. So the integers are connected. Sorry, is not connected. Integers are not connected. Connected in the real number line. And I'll just touch on a final one, the what's called the disjoint, the deleted, that's right, the deleted comb, which should just get your mind thinking a little bit further. Deleted comb space. So it looks a little bit like a comb. So let's draw the real number line. I'm sorry, not the real number line, Cartesian plane. Let's put here 1. And let's put up here 1. Now I'll start drawing what's part of the comb. So the first part of the comb we'll put here. So it just goes along there. So it goes along the x-axis. Yeah, that'll be fine. Here, and it'll include this one as well, that single point. Now it'll go up here to, we'll also include, where are we? There. We'll include, I'll touch this up in a sec. I'm going to have to hand draw it. Okay. So it'll include this line here, 1. It'll include a half. It'll include a third. Oh, a third would be about there. So these are just straight lines. I'm just drawing them funny. I should have done this beforehand. Let's move to it. So 1. And on it goes. So it's basically, firstly, it's 0, 1 times the point 0, and it's the point, it's also the point 0, 1, 0. And it's also the points 1 on n, 0 cross 0, 1, something like that. Look, anyway, you get the idea. So the question now is this connected? So the question we need to ask is, can we separate this? And it's tempting to say that we can separate it because we can go, well, let's do an open set. It's tempting to think that you can just do something like this. And the second one could be like this. Something like that, I don't know. But the problem here is that, of course, there is going to be things coming up here, the 5th, the 6th, the 7th, the 8th, the 9th, and they're going to cross, this is going to cross our open sets. So you can have a chance, I'll leave you to play around with this, but what you'll find is that there's no way that you can separate it. And, you know, you can prove these things that you can't separate them. I haven't done the proofs in what I've done, but it's possible to prove it. And, but I think if you just play around with it, you'll see that you can't separate it. So that's an interesting one. The interesting thing about this is that if you then move on to looking at path connected sets, well, path connected means that you can go from any point to any point, staying within the space. Now here you can see that you actually can't go from here to say this point here. Sure, you can go down here, but then you can't jump from here up to here. And no matter how many of these things that we have here, there's always going to be a space. So there's no way that you can go from here across this way to here. So this is an example you might see if you move on to looking at sets that are path connected. And in this case, it's connected, but not path connected. But just to be clear, this space, the deleted comb space, is connected because there's no way you can separate it. Okay, I hope that's started you on your journey through connectedness. If you've got any questions, let me know. And if I think I can help you, I will.